Hello, everyone. Happy Tuesday. I hope you had a great weekend. Okay, I hope and a wind doesn't affect you too much. But the good news is tomorrow it will, calm down. Calm down. The wind speed will be slower, and hopefully our wildfire down there in Irvine will get better. Will get controlled soon. Okay, so let me first share the screen. Let me first remind you what we had last time and your take-home message, the things you must know, okay? All right, so the most important thing last time is this one, okay? The global wind patterns. For local wind patterns, you always can use high-low pressure, right, to figure that out. High pressure give you cold air, descending air give you the high pressure, and rising air or warm air give you the low pressure, and wind always from high to low. Okay, so that can help you to explain many things. Land, sea breezes, right? Monsoon, okay? And also mountain and valley breezes. But for the global pattern, it's a little bit complicated. As you can see the picture on the right, we have three cells: polar cell, Faro cell, and Hadley cell. How they are created, right? Well, again, two reasons for high-low pressure: dynamic high, thermal high, dynamic low, thermal low, right? Okay, so you can see this equatorial low actually is a thermal low because they have low pressure. Why? Because air is warm at the equator. It's very, very hot. So the warm air, they want to rise, okay? Give you this equatorial low, okay? But when they hit the tropopause, they won't go, penetrate through the tropopause. So it's like you have a lid on top of your water fountain. The water will spread out, right? Will go to the two sides. So that is the upper level air in this Hadley cell, okay? But because gravity, because of Coriolis force, this upper air flow will be descending, will be drawn down to the ground, descending at about 30° north and south. So this subtropical high actually is a dynamic high, okay, because the air is still warm, subtropical, but just because gravity and Coriolis force, they have to be descending, so give you this high pressure, okay? And this subtropical high actually affect many, many regions, give those regions very dry weather because descending air, right? Including us, including our Southern California, including LA, especially in the summer when the subtropical high is very strong, you never see the rain, right? We have very dry, hot summer down here in LA, right? Okay, so this is a dynamic high. Okay, dynamic high. It's not because the air is cold. No. Okay, and you can see when this descending air striking on the ground, it's like a waterfall, right? When they hit the ground, they cannot go through the ground. They will be spread out. Okay, go to the two sides. And this one towards the equator give you this, surface wind from subtropical high to equatorial low. That is our trade wind. Okay, trade wind, high to low, deflect to the right, right? Southern hemisphere, same thing, but deflect to the left. Okay, so this basically is our Hadley cell, very important. Okay, rising air at the equator, hit the tropopause, spread out, and then because of Coriolis and gravity, descending, and then coming back. So this is our Hadley cell. Okay, I hope that makes sense. You can picture that. Okay. And this rising air, this branch of air go to the polar area, will be colliding. Okay, will collide into this, you know, cold air from our polar area. Okay, why you have this airflow? Well, this is the thermal high, guys, polar high, because it's very cold up there, right, in our polar area. So cold air descending give you this high pressure, and when they hit the ground, they just go to the lower latitudes. Okay, but things very interesting here. Okay, at about 60 degree north, about like Alaska. Okay, Alaska, or central part of Canada, that places. Okay, so you can see you have this cold air, you also have this warm air, and they collide. Okay, warm air is fluffy, is lighter, so they will be pushed up, right? Warm air will be pushed up. Warm air, well, here at itself also want to rise up, but it also kicked up, right, by the cold air from the polar area. So this will form a front, and rising air, you can see, give you this subpolar low. It's also a dynamic low. Okay, so when same thing, when it hit tropopause, it's go back and descending at 30 degree. So this is your ferrocell. Okay, and then the other branch go to the North Pole or South Pole, give you this polar cell. Okay, so I hope that makes sense. At this point, 30 degree, this one, this rising air is very important. That give us, especially the northern part of this country, okay, like Idaho, like Minnesota, very, very severe winters, okay? Not thunderstorm, snowstorm, okay? Blizzard, okay, like that. Yes, in the winter. Okay, I still remember my first year in Madison, the snow is to my waist, you know? I'm not tall, by the way, I'm 5'1", but it's to my waist, the snow. It just, it scared me. I'm like, Dad, I'm going back home. But this is the polar front. Polar front give you this polar low. Okay, all right. And then because you have polar high, subpolar low, subtropical high setting up like this, so your wind system, your vastalis, high to low, deflect to the right, right? Your polar easterlies, high to low, but deflect to the right of the wind. We need to turn ourselves around and to follow the wind and turn to the right. Okay, I hope that makes sense. Yes, good. Let me pause for other people have any questions. Wonderful, that's my scholars. Clear the drawings. But guys, let me tell you, let me confess. This is a model. This is a model to simplify the real world situation. Our real world never as simple, you know, straightforward like this. Okay, it's a chaos like this here. Okay, who messed this up? Okay, let me show you the picture. Okay, let me stop share. Okay, let me end my presentation and let me share you this picture. Okay, for example, this one. Okay, let me share the screen. Let me just share the entire screen so I don't have to go back and forth. Okay, do you see this picture here? Okay, so you can see, well, ideally, we should have high, oh, let me change the color. Annotate, let me go back. Okay, we should have, for example, this is our low pressure at the equator, right? Okay, to the north, 30 degree, we should have high pressure. What's the name? 30 degree. 30 degree.
Is that the subtropical high?
Exactly, Maggie. Very good job. Subtropical high. But you can see, no, we don't have a belt of high pressure, right? Instead, we have what? We have those high pressure only on oceans, right? Okay, same thing at the southern hemisphere. In the southern hemisphere, only on the oceans. Okay, this one is a exception because they're in winter. Let's just focus on northern hemisphere. Okay, this actually is the subtropical high. Okay, we also call that Hawaii high or Pacific high. This is the high pressure give us very dry summer. Okay, and this is we call that Bermuda high. Do you know all the mysteries, weird stories happen in Bermuda, right? It's called Bermuda high, okay? And it's another part of the Pacific high, okay? But you can see, well, this is summer in July. You can see our summer. You can see over our land, we actually have a low pressure, right? Over Eurasia continent, we have a strongest low pressure at that time. Okay, why? Can you think about it? Why in the summer, ocean is high pressure, but land is low pressure? We don't have high pressure. We cannot keep this high pressure over the land.
Because it's hotter?
Exactly, Nico. Professor Nico. Yes, you got it. Because land water heating difference. When we are talking about like this one, let me give you this picture, the 3-cell model, we assume what? We assume our entire Earth, we are all ocean. We don't have land. So we don't have to worry about land water heating difference. But in the real world, we have that, right? So the land masses actually can mess up your 3-cell model and our high-low pressure, the belt, okay? And earlier I say here in Australia, why in July they have a high pressure? Because there's winter down there in southern hemisphere, right? Okay, the tilt of the Earth, different seasons. Okay, so you can see we still have high pressure over the ocean because ocean is stable. Okay, they can maintain, but those high pressure get weakened because low. Weakened. Okay, and here actually over Brazil, okay, Argentina. Here we also have a high pressure over here. Okay, high pressure because it's cold. It's cold. Okay, and also you can see another weird thing is this dashed line. Okay, let me tell you, this one is called thermal equator. Thermal temperature, thermal equator. It's not the real geographic equator. Okay, this thermal equator, like the name tells, that is the hottest places on Earth in July. Okay, in July. So that is based on temperature. So when the places, as long as in the same longitude, they have the highest temperature, I will mark it, then I can connect them together. So this is basically the thermal line. Okay, the thermal line. So you can see compared to our real equator, real equator past Ecuador, Kenya, okay, Singapore, these places, you can see in July, our thermal equator is to the north of our geographic equator, the real equator. Why? The sun. Okay, Earth is tilted. In July, the direct sun rays, right, in your lab 2, direct sun rays is in the northern hemisphere. So that is the hottest place in northern hemisphere. Okay, so everything moved to the north, as opposed to, opposite, that is, winter, everything, the thermal equator will be a little bit below equator, about like this. Okay, so all these systems, they are shifting, and this can give you different weathers, different climate in different area, which we are going to study in after next module, climate. Okay, climate, the types. Okay, but I want you to give you this heads up. Okay, they're moving, they not just stay there. Any questions by far? Are we good? Wonderful. Wonderful. Great. Let me clear all my drawings. Okay. All right. Then let's see. Here. Go back to my slides. Okay. Then other things will be very, very straightforward. Okay. This just the Santa Ana wind. Here is a high pressure. Okay. Low pressure down here in LA, because early fall or mid fall, like now, our land is warm, is cold. So let me share with you. Yesterday I shared this with Diego. I want to share with all of you here. If you go to windy.com, okay guys, windy.com, you will see this amazing picture. Okay, so you can see those arrows actually show you the wind flow, the wind, the airflow. So you can see down here, we have very strong wind, and especially Santa Barbara. Okay, you can see this Santa Barbara. They call that sundowner wind over here. Okay, and you can see where they come from, guys, where they come from. From Nevada, right? From Nevada, because you can see this, I overlay the temperature. You can see over the land, the temperature is actually very, very low. Okay, because fall, land give up the heat very quickly, right? So you end up with a high pressure here in Nevada, okay, Vegas, those high pressure. But our ocean in LA down here, we're still quite warm, okay? Relatively warmer. So you will have a low pressure here, okay? So our wind, high to low, go to the right. So that is why now we have this Santa Ana wind, okay? Which make this wind so strong, so fast, and so dry. Our local mountains and desert. Okay, so first of all, let me change the color to draw the desert. Okay, you have your desert right here, right? Okay, you also have your mountains in between. It's a bad color. Let me change another color. Okay, these are our mountains. So when the air passes the desert, evaporation, they get drier and drier, right? When the air is rising, but then descending to LA, adiabatic warming, okay? You never see cloud formation. You have more evaporation that get very, very dry when they get to LA and Santa Barbara, this area, okay? And also very hot. Who speed them up? Are mountains, the valleys, the canyons. When they pass through those canyons, it's just like, a troop, water pass through those very narrow channels, and then they have to speed up, right? Okay, you have the experience when you go to downtown LA, when you're walking in between those skyscrapers, right? You'll feel very strong wind because they're squeezed into those narrow tunnels. Okay, so that is why yesterday, Sunday, it's so crazy. And of course, we have our ground, all the dead leaves, very dry plants. And if there's any spark, that will ignite the fire. will ignite the fire. Now here down Irvine, I have a friend, his family living there. The fire just 5 miles away from his house. I cross my fingers for the family every day. So about like half of the urban get evacuated. You know, you have to leave your house, you know, temporarily. Okay, we actually call those people, if they have to leave permanently, we call them climate refugees. Climate refugees. Because of climate change, you have to leave. You have to find a new place to live. Okay, so that's no joke. It's not kidding. It's serious. But where you should move to and who need to pay, right, for the moving the fee. So you can see climate and our society actually they are very closely connected. Okay, and our life, especially your future. I just you know, so proud of you guys, you know, last year and including this year, you have the climate strike. You fight for your future. That's the right thing to do. Okay, that's the right thing to do. Okay, so let me go back. Stop share. Then let's see. I have a video for you. Let me find out video. History. Actually, that one is on your study guide. Okay, so let's see. Oh, let me share first. Okay, then let's talk about jet stream. Okay, let me share the picture, share the screen. Okay, here we go. Okay, so this so-called jet stream, let me present. Okay, that is first, that is your upper level airflow. Upper level airflow. Okay, so we actually have 2 jets in each hemisphere. So you have 2 in northern hemisphere, you have 2 in southern hemisphere. So in total you have 4. Okay, but now let's just focus on the jet stream in northern hemisphere. Okay, so you can see you have 2. One is called change the color. Okay, green maybe. Okay, subtropical jet stream because it's over about like 30° north and south. Subtropical jet stream, but it's upper level wind flow. So what I'm talking about is this one, subtropical jet. Okay, how it is created? Well, you know, this is our Hadley cell, right? Now we change the perspective. We see on the ground the cross section from sky to the ground. Okay, so you can see at the equator, warm air rises, right? Heat the tropopause, need to spread out. Okay, but when this air flow going to the north, if you can picture that, you follow the airflow, you need to be turned to the right, right? Okay, so this arrow, if I can show you the 3D, later you will see the 3D, well, will be moving into our computer screen. Okay, moving into our computer screen. So this is your subtropical jet. Subtropical jet. Okay, part of it moving into, you know, into our computer screen, and the other one, you know, eventually, you know, dragging will be descending to the ground, give you this subtropical high. Make sense? Okay, but we don't worry this one too much, especially in our area. You know, we are about 30, we are 34, right? Because one reason you can see it's very high. It's quite far away from us. I will say like 10 kilometers like that, okay? We'll have very little effect on the ground, okay? Down to the ground. But we more consider about this polar jet. It's also an upper wind flow. And who created? Well, you can see this descending air, they hit the ground, they need to go to the north, right? And they will be pushed by this cold air from polar area, give you this polar front, right? But when this air is rising, also affected by coriolis force. So when it's rising, like you climb the mountains, you have to be deflected to the right. So also into our computer screen. Make sense? Can you picture the 3D? Okay, you move up, but you need to turn to the right. So this is the polar jet. But this polar jet has more, impact on the ground at 60° north and south. Because number one, it's very close to our ground. Okay. Number two, when it's rising, it gives us a lot of rain and snow. Okay. And don't think 60 degrees far away from us. No, that can affect whether you can eat Russell potatoes. Okay. In Idaho. In Idaho potatoes. Okay. If this polar jet gets super, super strong, well, our potatoes, the price will increase. Okay, so you can see this is the formation of the polar jet. Okay, but again, you can see this is the polar jet. Okay, polar jet stream. But you can see this polar jet is not just a line, right? They have the rivers. They have those meanders. Well, why? Because our high-low pressure system is messed up by our land water heating difference. You have those cells, you don't have a belt. Okay, so that creates this meander. We actually call that Rossby waves. Okay, Rossby waves. Let me show you here. Clear the drawings. You can see cold air from the north, right? Let me change the color. Okay, change the color to red. Okay. Oh, sorry. Okay, here we go. Oops. Okay. All right. Okay. So this is the cold air from the north, right? Because our land water heating difference. For example, this is our winter. You can see this one. Okay. This is our winter in northern hemisphere, and it's super, super cold. Okay, and you can see this is Canada and our the northern part of this country, right? You can see United States, Florida down here. Okay, this cold air actually can go down all the way almost to Texas, Arizona. Okay, and our warm water, okay, can go all the way to the north to Alaska. And then you will have this huge descending, okay, in your Rossby wave. Okay, we call that a meander, like a meander in the river. Okay, and sometimes this cold air will become so strong, they will be, break out from this giant cold air and descending all the way to Mexico. No joking. Okay, so this is the weather, severe weather, the winter, very strong winter storm, okay, moving down to our country, to even go to Mexico. So you can see in this picture, you see this very exaggerated meander down here. Okay, that's just because this part of the cold air gets super, super strong, as opposed to this part of the warm air gets very, very strong. So you have this big contrast. They basically tortured, disformed this meander. Does that make sense? Okay. All right, then let me share with you this very helpful video to help you visualize this jet stream in 3D. Okay. Let's see. I need to go back. Come on. Let me stop share. Every time I cannot see that. Okay, here we go. All right, let me share this.
are another name for fast-flowing currents. Jet streams are another name for fast-flowing currents of air. There are many different jet streams that exist at both high and low levels in the atmosphere. Each has an important role to play in the weather experienced on Earth. The major jet streams that circle the Earth are found just below the tropopause at a height ranging from 9 to 16 kilometers and can reach speeds over 200 miles per hour. They are hundreds of kilometers wide, but only a few kilometers deep, so are often described as a ribbon of very strong winds. The major jet streams are the polar front and subtropical jets. These occur in both the northern and southern hemispheres and are part of the larger global circulation. The polar front jet occurs over mid-latitudes and strongly influences the weather over the UK and Europe. The polar front jet is a type of thermal wind that arises due to the strong temperature contrast between cold polar air and warm tropical air. To explain this further, imagine two columns of air, one in the cold air to the north of the jet and one in the warm air to the south. The top of each column is bounded by the tropopause. A shorter column of cold air exerts the same surface pressure as a taller column of warm air. This is because in the cold air column, the air is more dense. This causes atmospheric pressure to decrease more quickly with height. In the warm air column, pressure does not decrease as rapidly with height because the warmer air is less dense. The tropopause in both columns is at the same atmospheric pressure. So if you were to climb to the same height in both columns, you would find that you would be at a lower atmospheric pressure in the cold air column and a higher atmospheric pressure in the warm air column. The pressure difference caused by this temperature gradient produces a pressure gradient force.
Okay, so I know this part a little bit confusing. Let me explain. Okay, let me explain. So you can see here, this is the warm air from subtropical. This is the cold air from polar. Why here we have a high pressure? Well, make things simple. Actually, it's very easy. I think this video overcomplicated. Okay, rising air. Right, this is not rising air. Okay, warm air is rising air, right? Right. So the air column will be taller. So if you standing here, the same level, remember we always compare the air pressure at the same level, you will have more air molecules in your area, right? Striking on you that create this high pressure, okay? Because you have the rising air, you have the rising air, okay? You will have more air molecules if you're standing here, as opposed to here. If you're standing here, since the air itself is cold, air, instead of rising, actually they want to descend. They want to descend to the ground. So in your area, this little guy, they don't have that much air molecules. You can see this air column actually is very, very low, right? Very short, as opposed to this one is very tall. Okay, so that is why upper level, okay, don't get me wrong, lower level at the ground, you still have a low pressure at the ground, you still have a high pressure at the ground, okay, but upper level at tropopause, okay, close to the tropopause, well, you will see this warm air column actually give you high pressure, this one give you a low pressure, upper level, okay, upper level, this due to the airflow. So you can see that is why you have this wind. Okay, you have this wind. Does that make sense? Okay, okay. I hope that helps. I know it's a confusing part.
So
okay,
the air pressure,
yes.
The air pressure depends on the altitude.
Well, here, let me correct.
Okay.
If you want to compare the air pressure, make sure you compare the air pressure at the same level.
Oh, okay.
Okay, yes. Okay. All right, so let's keep going.
The pressure gradient force acts from high to low pressure, so theoretically in the northern hemisphere, air would flow from south to north. But the Coriolis force resulting from the Earth's rotation causes the air to move to the right of the direction of motion in the northern hemisphere and to the left of the direction of motion in the southern hemisphere. In both hemispheres, the jet stream flows parallel to this temperature gradient, moving from west to east. Theoretically, this jet encircles the Earth in a continuous line, but in reality, it is more broken up, as differential heating of land sea masses lead to west to east temperature contrasts as well as north to south. As the polar front jet forms due to the temperature contrast, the stronger the temperature gradient, the stronger the jet. This means that the jet is stronger in the winter than the summer as the poles cool during the winter months, increasing the temperature contrast. In the northern hemisphere, the jet tends to be further south in winter and further north in summer. This is due to the tilt of the Earth, and that in the winter, the northern hemisphere is tilted away from the sun, and in the summer, it is tilted towards the sun. Mid-latitude low-pressure systems occur on the polar or northern side of the jet stream, while more settled, warmer conditions are found to the south. This gives us the wet and windy weather we often see in the UK during the winter months, as low-pressure systems are steered towards us. It can also lead to some disappointingly wet summers if the jet stream remains to the south of the UK. A stationary jet stream pattern will bring frequent low-pressure systems to the same region. When warm air moves further north and...
Okay, so let me go back a little bit. Okay, oh, here. Okay, so people, you can see this is Diago's question. I bet it's most of you have the same question. Jane, here I know polar area we should have cold air, but why we have this low pressure system? This actually is a dynamic low. Okay, you have this cold air. Let me use a blue color. Okay, you have cold air up here, right? You have the warm air down here, but those low pressure system is created by this rising warm air, dynamic low. It's pushed up by your very strong cold air. Okay, so that is our subpolar low, polar fronts. Okay, I hope that makes sense. So don't just think every time you see low pressure, that's because warm air, that's because the air is rising. Okay, more importantly, that is air is rising. Every time you see high pressure somewhere, that could be two reasons. Air is descending or air itself is cold. Does that make sense? Okay, wonderful. Okay.
Systems to the same region. When warm air moves further north than normal, or cold polar air moves further south, this can change the prevailing west to east jet stream pattern. This causes the jet stream to buckle, driving depressions towards different regions or blocking their movements altogether. A straight west-east flowing jet stream won't have much impact on the development of new weather systems or strengthen pre-existing ones. When a jet stream meanders north and south, air accelerates and decelerates around the bends in the flow. These areas of changing speeds are our development areas. Where the air is accelerating, more air is leaving than entering a certain point. This means that the air is being depleted at this point. To fill this depletion, air from below rises. When air rises, it forms clouds and precipitation. Winds at the surface converge to this rising air column, which causes surface pressure to fall, and a low pressure system may develop or deepen further. So whilst a jet stream is just an area of fast flowing air, it has a fundamental effect on our weather.
All right, so don't worry too much about this last part, why the low pressure system will be feeding the jet stream. We will learn that in the next module when we study the severe weathers. More specifically, that is your mid-latitude cyclone. Okay, that low pressure actually on the ground is triggered by that jet stream. Okay, jet stream is super, super important actually. Okay, all right, so here, any questions, guys? Good. All right, okay. So let me save the currents next time because I do want to give you a start on our labs, okay? So let me share the lab document. Here, labs, lab 4, okay? You can download it on our Canvas, okay? Oh, should be 20, sorry. 20.h. Okay, so the first question really just tests you one thing, pressure gradient, how to calculate it, okay? So this is the formula you are going to use.
We can't see the lab.
Oh, you can't see the lab?
No.
Okay, so let me stop share. Share the screen. Do you see it?
Yes.
Okay, you see the, did you watch the videos? Yes, right? That scared me. Okay, so here. This is your pressure gradient force. So basically you use the high pressure minus the low pressure divided by the distance between high and low. Okay, so that's your gradient. That's your gradient. So for example here, the first one, you have those two places, Greenville and Franklin, right? Which part you have a high pressure? Which part you have a low pressure? And what's the difference in between? Okay, so that is your pressure gradient force. Okay, your pressure gradient force. Show your work, please. I think the first question is straightforward, okay? And I want you to relate this pressure gradient with wind speed, okay? If you have a higher pressure gradient, you have a high wind or low wind, okay? Strong wind or weak wind, okay? All right, and then let's see. Okay, so this one is more, is similar to our jet stream, okay? I want you to study the local wind pattern. So you can see we have two places. We have our city, think about LA. Then we have our village. Think about Santa Monica, suburb. Think about Santa Monica or other rural area, okay? So you can see city because you have this, urban heat island, right? Usually over the city, the air is warm. So the warm air want to rise, okay? And cold air, they want to sink over the rural area, okay? Because they don't have this urban heat island effect, okay? So if you have the air rising up down here, but descending here, on the ground, you have a high pressure or low pressure. And then determine the wind is going this way or going this way. I don't know. You need to figure that out. Okay. And upper level, think about this aloft is your tropopause. Okay. If you're receiving rising air in this area, is high pressure or low pressure? If the air is descending from here, you have a high pressure or low pressure. Okay, and then help me determine the wind to which direction, which way they should go based on the same level air pressure. Okay, all right, I hope you have some idea. Okay, and let's see. All right, Then this is a real world example, Santa Monica, to study the land sea breezes. Okay, so you can see I give you the temperature at two places. One is this solid line. That is the temperature I recorded, not I recorded, the weather station recorded in Santa Monica at Santa Monica Pier. Okay, and you can see, well, actually we have relatively low temperature, okay, at noon, right? At noon or afternoon. And you can see this dashed line, that is your Santa Monica Airport, okay? And then you can see here, of course, over the land, we have the highest temperature. You have the delay, you have the lag, right? Afternoon. So you have a big contrast in the afternoon, okay? And then I want you to read this chart, figure out what's the time of the high-low temperature, and based on that temperature, okay, figure out high-low pressure and to figure out the wind direction, the land sea breezes, okay? So if you are interested, you actually can see the real-time temperature at two locations now, following those links, okay? All right, okay. Then I think today, let's just start with those three questions, okay? Let's save the rest of the lab next time, okay? Because you will be drawing the wind and also the isobars, okay? And the last one basically is your El Nino, okay? And next time I will give you a very interesting video about El Nino, okay? All right, okay, so let me stop share. Let's just focus on three questions this time, okay? Well, I think today you probably just have time to meet your friends, meet your group mates. Okay, so let me first stop recording.